Welcome back. In this lecture, we will cover the Bernoulli equations and its applications. Fluids have been an important source of energy throughout human history. Sailboats and sailing ships have been around for more than 5,000 years. A Greek engineer, Heron of Alexandria, has captured the power of wind using windmill that was part of one of the earliest examples of the musical instrument called organ. In this windmill would rotate, would pump air into this organ, so the organ would sound. Wind-driven prayer wheels. A prayer wheel is a cylindrical wheel on a spindle made of metal or wood. Traditionally, the mantra Om Mani Padme Hum is written in Nevari script of Nepal on the outside of the wheel. At the core of the cylinder is a live tree with mantras written on or wrapped around it. According to the Tibetan Buddhist tradition, spinning such a wheel will have much the same meritorious effect as reciting the prayer. Windmills used to drive the flour mills were quite common in Dutch and English countryside in 12th century. Modern day windmills are quite big. For example, this MHI Vestas has a rotor diameter of 164 meters compared to the height of Qutub Minar, which is only 71 meters. This is a self-contained power generator. The control box at the hub of the windmill is a passenger bus sized container which contains, among other things, a generator. It contains a yaw controlling device that orients the windmill such that it faces the wind. It also contains a device that adjusts the pitch of the blades so that the optimum power can be generated. This windmill, which is among the largest in the world, produces 9.5 megawatt at its peak power. Prayer wheels run by flowing water are quite common in northern India. There's a picture from Spiti Valley in Himachal where a prayer wheel is run by a stream of water. Water wheels have been used in Europe for the purposes of milling corn, for running hammers, etc. The various kinds of water wheels that date back to 1st century before Christ. The design of these wheels have been changing ever since. The modern hydroelectric power projects have water wheels at the core of them. One of the common design is the Pelton wheel, which was patented in USA in 1850. This is the picture of the Pelton wheel used in Hoover Dam in California. It uses buckets for generating the powers. When a jet of water plays on these buckets rotate. One such wheel can produce up to 2.5 megawatt of power. In both wind and hydraulic wheels, the mechanical energy of the flow is extracted as work done. And so, the first law of thermodynamics, dE by dt, is equal to Q dot minus W dot for a system is applicable. Here E represents the total energy of the system, which includes the mechanical energy there is kinetic and potential energies together, and the internal energy associated with the random motion of the molecules. If gravity is the only body force acting on the system, this specific energy, which is the total energy per unit mass, is given by V square by 2 plus Gz plus U. So, for a system, the capital E is the total energy, which is the integral of this E over the whole system, and Q dot represents the rate at which the heat is transferred to the system, and W dot is the rate at which the work is done by the system. Q dot is positive when it is transferred to the system. W dot is positive when it is done by the system. Let us consider a control volume, a device with one inlet and one outlet area. The total energy content of this is this specific energy times the mass integrated. The rate of change of total energy contained within this control volume is given by the Reynolds transport theorem as the local rate of change of energy contained within the system, that is the rate at which the energy accumulates within the system, plus the rate at which the energy leaves the control volume, minus the rate at which the energy enters. If rho A V is the mass rate at which the mass enters the system, then rho A V times E, evaluated inlet, is the energy that enters the system. Similarly, rho A V E at outlet is the energy rate at which the energy leaves the system. For steady flow, the rate of accumulation is 0, and so dE by dt, the material rate of change of energy associated with the control volume, is nothing but the net outflux of energy from the system, and which should, by first law of thermodynamics, be Q dot minus W dot. Q dot, the rate of heat transfer, is the diffusive heat transfer across the control surface, and this is because of heat conduction, which is due to the temperature difference at the control surface between the matter inside the control surface and the matter outside the control surface. In this presentation, we'll assume this is negligible. So dE by dt is nothing but minus W dot, the rate at which the work is done by the system. Net efflux of energy out of the system is nothing but minus W dot. Let's begin with a very simple situation. Let us consider a streamline within the flow. The flow is taking place along the streamlines. Let's mark 2 points, 1 and 2 on the streamlines. Let's take a control volume. And what do we take as a control volume? We assume a small stream tube with a narrow cross section running along the streamline. Since this is a stream tube, no matter crosses the surface. So if we take this as a control volume, the matter is entering only at the cross section 1 and leaving at cross section at 2. Let's make the following assumptions. Obviously, point 1 and 2 are on the same streamline. We assume the flow to be steady. We assume the flow to be incompressible. That is, we assume the density to be constant. We also assume the flow to be inviscid. No shear stresses, no viscous action. Also, let us assume there is no thermal action within the fluid. That is, no heat generation within the fluid, no heat transfer, and consequently no change in temperature of the fluid. If there is no change in temperature, the value of U, the internal energy, remains unchanged between point 1 and point 2. So now the first law of thermodynamics reduces to the net efflux of energy across point 1 and 2 is equal to minus of the net work done by the system. Let us now consider the work done. Work done by shear stresses. First of all, there are no shear stresses. We assume the flow to be inviscid, so there is no work. Work done by normal forces, which are pressure at the inlet and outlet, can be determined thus. At the inlet, the force of pressure is P1A1 and the velocity of the fluid is V1. So the rate of doing work is P1A1 V1. Is this the work done by the system or on the system? Clearly, this is the work done on the system because this pressure is pushing the fluid into the control volume. So this is negative. That's why we have put a negative sign in front. At the outlet, the pressure is P2, the force is P2A2, and the velocity is V2. So the work done by pressure forces at the outlet is P2A2 V2. This is positive since it is the work done by the system on the surroundings. So the energy balance equation is this, in which we notice that rho AV at outlet is equal to rho AV at inlet because of mass balance. And let's write this as dm dot, the rate of mass throughput through the system. And if we use this in the energy equation, we get W dot, which is P2A2 into V2 minus P1A1 into V1, and it can be written as P2 dm dot divided by rho 2 minus P1 dm dot divided by rho 1. This W dot, the net work done by the system. And using this in the energy equation, the specific energy E2 at the outlet times dm dot, the rate of mass throughput, minus E1 times dm dot is equal to P2 dm dot by rho 2 minus P1 dm dot by rho 1. We can cancel out dm dot throughout, and for E is equal to V square by 2 plus Gz plus U. This gives V square by 2 plus Gz plus U plus P by rho has the same value at the outlet as at the inlet. Further, since we assumed that U does not change, there is no change in temperature of the fluid, this equation can be reduced to V square by 2 plus Gz plus P by rho at the outlet is the same as at the inlet. This is known as Bernoulli equation after the scientist who discovered it. This is a very useful equation and used extensively in fluid mechanics. In the next couple of lectures, in this lecture, we would be interested in applying this equation to various situations. It is so commonly used that many times we make wrong applications of this equation. Notice that this equation came with a lot of conditions, a lot of assumptions. If any of these assumptions is not met, the equation cannot be applied. To reiterate, the energy V square by 2 plus Gz plus P by rho per unit mass is the same as outlet and inlet of a controlled volume if the 2 points are on the same strip line, the flow is steady, the flow is incompressible, the flow is inviscid, and that there is no thermal action within the fluid, no heat generation and no heat transfer. Notice that we have not used the condition of incompressible flow explicitly in this derivation, but this comes in indirectly, because if U, the internal energy, is not changing and the flow is inviscid, then there cannot be any change in density if there is no heat transfer. So, once again, V square by 2 plus Gz plus P by rho is a constant along the streamline if the flow is steady, the flow is incompressible, the flow is inviscid. There is no energy extraction or energy supplying device in the system between points 1 and 2. We had not stated this earlier, but this goes without saying, and that there is no thermal action within the fluid. We had introduced the concept of pressure heads earlier when we were discussing fluid statics. Now, in this Bernoulli equation, each of the term V square by 2, Gz and P by rho represents energy per unit mass with the units of joules per kilogram or meter square per second square. If we divide across by g, the acceleration due to gravity, we get V square by 2g plus z plus P by rho g. Now, each term has a unit of meter, dimension of length, and each term represents energy per unit weight of the fluid. The units are joules per Newton or simply meter. Each of them is termed as a head. V square by 2g is the velocity head, z is the elevation head, and P by rho g, as we discussed in fluid statics, is the pressure head. Z plus P by rho g, that is the elevation head plus pressure head, is also given the name piezometric head, and that together with V square by 2g is the total energy head. Using head as a unit of energy is very common in the practice of civil engineering. Let's talk of a piezometric head a little bit more. Suppose there is a tube through which a fluid is flowing, as shown. At the point marked with a black dot, the column in a vertical tube conducting with this flow is the pressure head, is the height to which the fluid would rise. This tube is called a piezometer, and if h is this height, h clearly is P by rho g, the pressure head. The height of that point above an arbitrary datum, z, is the elevation head, and the sum of the two is the piezometric head. Let's now apply Bernoulli equation to a very simple situation. Consider a tank in which a liquid is present to height h. There is a free surface of the liquid at height h. exposed to atmospheric pressure. So the gauge pressure at the free surface is 0. There is an orifice in the tank at Z is equal to 0. That is at the bottom of the tank of area A. What is the rate at which the fluid issues from this orifice? We may apply Bernoulli equation, but for Bernoulli equation we need 2 points along a streamline. There must be a streamline running something like this, a point 1 on the surface to a point 2 at the orifice. It may not take exactly this path, but a similar path between point 1 on the surface, anywhere on the surface, and a point 2 at the orifice. Now, let's apply Bernoulli equation. Let's look at the conditions required. The 2 points should be on the same streamline, which they are. We have chosen them to be on the same streamline. The flow is steady. Really is not steady. As the fluid flows out of the orifice, the level at point 1 would drop. But if the orifice is much smaller than the cross-sectional area of the tank, the rate at which the level drop would be very small compared to the flow velocity. So the flow can be taken as quasi-steady, not truly steady, but for the purposes of applications at any given instant, it may be assumed as if the flow is steady, quasi-steady. The flow is incompressible. We are assuming a liquid, so the flow can be assumed to be incompressible. The flow is inviscid. Let's assume this to be inviscid. Any deviations would come as an error. We will discuss much later that the viscous stresses would be very small in this flow, but that is for later. There is clearly no energy extraction, energy supplying device between points 1 and 2, and there is no thermal action within the fluid. No heat generation and no heat transfer. So, the conditions required for application of Bernoulli equations seem to be satisfied. And so, total energy at the outlet must be the total energy at the inlet per unit mass. Let us consider the value of these. V1 square by 2G is equal to 0 approximately. We have said this before. The level is decreasing at very slow rate, at negligible rate. P1 is P atmosphere. Z1 is H. P2, the pressure at the orifice, is again atmospheric, and Z2 is 0. We have to find out V2, and simple application gives you V2 is equal to under root 2GH as we plug in the above value. This was an expression obtained by Torricelli, an Italian scientist. The velocity at the outlet varies at square root of H, the level of the liquid within the tank. So what is the volume flow rate of the fluid out of this orifice? V2 times the area of the orifice, A2. This picture shows a jar with orifices at various heights. At the topmost orifice, the jet is the weakest. At the bottommost, it is the strongest. Let us now extend this a little further. Let's assume that the jet that issues out of point 2 falls down, and we can show easily that this would follow a parabolic path and falls down through a distance h, a lowercase h, up to point 3. Can we find out what is the velocity at point 3 and what is the area of the jet at point 3? Clearly, all the conditions would still be met, and we can apply Bernoulli equations between point 1 and 3 directly. And if we apply, V3 would come out to be under root twice g into capital H plus h. The velocity would increase as the jet falls down. But the cross section of this jet would decrease. Why would it decrease? Because of the mass balance. The mass flow rate through section 2 must be same as mass flow rate through section 3. And since velocity at 3 is more than velocity at 2, the area at 3 should be less than the area at 2. Let's consider one another extension of this problem. Let's attach a tube to the orifice of the same area A2, and this extends up to point 3. Now the flow takes place within the tube from 2 to 3. And so, if we apply the equation directly between point 1 and 3, we'll get the same velocity 3 as before, as in the last slide. V3 is equal to under the root 2g into capital H plus lowercase h. But now the area is larger. Area has not decreased. The velocity here is V3, and the area would be same as A2 because we have used a tube. The tube is full. So this is the way you can increase the flow rate from the tank. Attach a tube and bring it down to a lower level. Let's consider this phenomenon as siphon. If the tube connecting the two reservoirs is full, then the liquid with a higher level of fluid empties into the tank with the liquid at lower level. How do we analyze this? To analyze this, let us consider the arrangement shown here. There's a liquid in the tank, and there's a tube that runs from the tank, goes to a maximum height h3 above the datum, and goes down to a distance h5 below the datum. There would definitely be a streamline, something like what we have shown here, 1, 2, 3, 4, and 5. Let us apply Bernoulli equation between the various points on these streamlines. This table organizes this determination. At point 1, on the surface of the liquid, on the free surface of the liquid in the tank, pressure head is clearly 0, the pressure being above the atmosphere, that is the gauge pressure, since the pressure at 1 is atmospheric. Clearly, P1 is 0, P1 gauge is 0, so pressure head is 0. The elevation is 0 because we have taken the datum at that height. The velocity head is 0 because the velocity is negligible if the tank area is large, and the total head is 0 as in this row. Next we consider 5. Why 5? Because we know 2 of the 3 heads at 5. We know the pressure head to be 0 because the pressure at the exit is also atmospheric. We know the elevation head, which is minus H5 now. And since the total head must be 0 as required by the Bernoulli equation, we can determine the velocity head. And the velocity head simply would be what? H5 plus H5. Because the elevation head is H5 minus H5, the total head is 0, so the pressure head must be H5. So the velocity head must be H5. As long as 0.5 is below 0.1 and the siphon tube is running full, there would be a positive velocity at H5 downwards. Then we move on to 0.2. What do we know here? We don't know the pressure, this is inside the pipe. But we know the elevation head, which is 0, and we know the velocity head. Why? Because mass balance between 0.2 and 5 would give you the same mass flow rate, and if the area of the tube is constant, then the velocity must be same. So H2, so the velocity head at 2 would be same as velocity head at 5, and velocity head at 5 is H5, so velocity head at 2 is H5. The elevation head is 0, and since the total must be 0, this means the pressure must be minus H5. There would be a vacuum pressure at 0.2. The pressure at 0.2 would be less than atmospheric inside the pipe. Interesting. Then we go to 0.3 at the top of the siphon tube. At this point, the total head by Bernoulli equation must still be 0. The velocity head must be same, H5. All across the tube it is same. Velocity head is H5. The total head is 0. The elevation is H3 now. So calculating this is determined, the pressure head is determined as minus H3 minus H5 to make the total head 0. Let's try one more. 0.4 at the same level as 0.1, the free surface in the tank. The elevation head is 0. The velocity is same, so velocity head is H5. The total head required is 0. So this means the pressure head should be minus H5. All right? We have been able to find pressures everywhere in this tube. The pressure is at 0.2, the pressure is subatmospheric. As we go up the tube, the pressure decreases. The minimum pressure is at 0.3. And then as we go down the other limb, the pressure increases and increases to 0 value at the exit of the tube at 0.5. If we plot this, let us take this to be the 0 line. The elevation head, 0.1, 2 and 4 are at the datum, so the elevation head is 0 here. 0.3 is H3 above the datum, H3 above the datum, and 0.5 is H5 below the datum, to the left in this diagram. The pressure heads we plot. The pressure at 1 is 0, and so is the pressure at 0.5. Pressure 1, 0.1 and 0.5, both pressures are 0. Pressure at 3 is minimum, and pressure at 2 and 4 is minus V square by 2G. This is the velocity head minus V square by 2G everywhere throughout the pipe. Throughout the pipe, the velocity head is minus V square by 2G. This is also the piezometric head. Minus V square by 2G is a piezometric head. To this we add the velocity head to get the total energy head. And the piezometric head is minus V square by 2G. To this we add the velocity head of V square by 2G, and we get a total head of 0. So this is the total head throughout the tube. When would a siphon not work? You see, the lowest pressure is obtained at 0.3. So the siphon would stop working when the pressure at 0.3 is such that the water boils, that the cavitation occurs. And when would the cavitation occur? When the pressure becomes equal to or lower than the vapor pressure of water. So depending upon the temperature, the vapor pressure of water is quite low, a few kilopascals. So this sets the limit of when the siphon would work. If we neglect the small vapor pressure, then we may say the siphon would work till at 0.3 there is total vacuum. The pressure becomes absolute 0. This means the height H3 plus H5 is equal to the barometric head, the atmospheric pressure converted into the liquid head. If liquid is water, then this is about 10 meters. So if the long arm of the siphon is about 10 meters, the siphon would not work. So we can empty a tank only if the long arm of the siphon is less than the barometric head, which is about 10 meters for water. Many of the flushing cisterns in your toilet work on the principle of siphon. There is a cistern that holds water because of a float valve, and there is a siphon tube that runs like this. The water level is maintained at a level up to here such that there is air on top at the siphon tube. Now as you operate the handle, this big plunger is moved up. As it moves up, it displaces water inside this tube, and the water level rises and it completes the circuit. The water level rises and flows down, and once this tube flows full, it will not stop till all the water in the tank or the cistern is emptied. And so this results in a flush in the toilet. Let's consider another example, a little more complicated example. of a natural draft in a chimney. Suppose we have a fireplace and a chimney to supply it air. And we let the natural draft do the supplying of air. How does it do it? Let's assume that the air flows across from 1 to 3 to 4 and then to 2. Point 1 is at the inlet of the chimney. Point 2 is at the outlet of a chimney. We can assume the velocity of A at point 1 to be nearly 0 because of large area. Let's assume the fire zone is a constant pressure fire zone in which the pressure does not change. So the velocity would be same, the air would be heated, the density would be lowered. Let's apply Bernoulli equation between point 4 and point 2. Point 4 just after the fire zone and point 2 at the exit of the chimney of height h. The equation of Bernoulli would be V2 square by 2g plus P2 by rho g plus Z4 plus h should be equal to V4 square by 2g plus P4 by rho g plus Z4. Z4 is the elevation of point 4, which is 0 here. P4 is like P1. Pressures are same. But pressure at P2, how do we obtain that? Now, let's assume that the gas is heated, the pressure is same, so the density would be lower. Let the density of gases within the chimney be rho, while the density of gases outside, the air outside, is rho naught. Pressure at 2 is determined from the external atmosphere. So pressure at 2 is P1 minus rho naught GH. Rho naught is the density of air in the atmosphere. Going up the height h, the pressure will reduce by rho naught GH. Rho naught is greater than rho. Then V4 is A2 V2 by A4. If we plug in the values in the Bernoulli equation, we get V2, the velocity at the exit of the chimney, to be this expression. Here you know the velocity depends directly as a square root of rho naught by rho minus 1. It only works if rho naught is more than rho. If rho naught is equal to rho, that is, the temperature inside the chimney is the same as the temperature outside, so that rho naught is equal to rho, then this velocity would be 0. We also notice that the velocity varies like under root h, the height of the chimney. The more the height of the chimney, more is the velocity. A typical case is when A2 is much smaller than A4. The area at the fireplace is much more than the area at the exit of the chimney. So A2 by A4 is very small, so the denominator can be replaced by 1, and the velocity at the exit of the chimney is simply under root twice of rho naught by rho minus 1 times GH. Depending upon how much flow of air we want across the fireplace to keep the fire going, we can determine what should be the height of the chimney. This is an interesting example, a Heron's fountain, in which you see the water is being thrown above the level of water, the highest level of water contained within the tank. Why is this happening? From this tank, the water is flowing down into tank 3. Because of this water flowing down to 3, the pressure of air within 3 is increased. The pressure of air within the 3 is communicated to air at 2, and the increased pressure at 2 pushes the water up this tube, and the water can rise above the level of water in tank 1. A simple construction of Heron's fountain from used water bottles. Bernoulli equation can also be used to calculate the flow velocity in a pipe. Consider a liquid flowing through this. We use a bent tube aligned with the flow. In the lower end is aligned with the flow, and the upper end rises vertically. Because of the energy of the flow here, the water rises into this tube. This bent tube is known as the Pitot tube, after the French scientist who invented it. There is also a simple piezometer attached here to the wall of this tube, and the water rises in this tube to the height of piezometric height. Now, to calculate the velocity of the flow, assume a straight streamline between point 1 and 2. At U, the point 2, which is directly at the entrance of the bent Pitot tube, there is no flow taking place. So the velocity at point 2 is 0. And if we assume the velocity at point 1 is the velocity of the water flow, this velocity V or V1, then the Bernoulli equation gives you V2 square by 2G plus P2 by rho G plus Z2 is equal to same quantities with subscript 1. Here clearly Z1 is equal to Z2. The velocity at point 2 is 0, V2 is 0. So V1 is given by under root twice delta P by rho, where delta P is the pressure difference. By applying the hydrostatic rule, we can find out that P2 minus P1 is nothing but rho G times delta H, where delta H is the difference in level between the piezometric tube and the Pitot tube, so that the velocity at 1 is given as under root twice G delta H. This Pitot tube is used for velocity measurements very extensively. Almost all aircrafts measure their velocities through use of a properly designed Pitot tube. We will discuss more of this in later chapters. There are special names given to these pressures. P1 is named the static pressure. P2 is named the stagnation pressure, because this is the pressure where the flow has come to rest. The flow taking place along the streamline 1 to 2 has come to rest at point 2, is stagnating at point 2. So that's why P2 is termed as the stagnation pressure. And the difference P2 minus P1, which by Bernoulli equation is nothing but 1/2 rho V1 square, is termed as dynamic pressure, the pressure because of the velocity of the fluid. Dynamic pressure. Thank you very much.